Okay, so our next speaker is Samuel here from Svenska Kraftnät, and it's very exciting to have them here. Feels like very relevant right now to hear about this. You're going to talk about renewable energy transition, and it's going to be exciting to hear what you have to say, and seems like it's never been a better time to talk about the power grid.
Yeah.
So big applause for Samuel. Yeah, and welcome.
Thank you. Hello everyone. My name is Samuel Eliasson Godonou, and I work as a consultant at One Group, Stockholm, and I have been assigned as a data scientist at Svenska Kraftnät, or SVK, for the past 1.5 years. And today I will talk to you about keeping up with the renewable energy transition using Python and forecasting to maintain a balanced Nordic power system. So one of the challenges with the energy transition is the increased share of renewable energy sources. And one of SVK's approaches to this challenge is the developing of forecasting tools for the control room with the help of the data science team. And today I will talk to you about the challenges of the energy transition and what my team in the data science group are doing to make the transition smoother and better. So as the energy landscape changes, we are transitioning from a mix of plannable energy production types to more weather-dependent and non-plannable production types, as wind power and solar power. And also there are big changes to consumption of energy, for example, the increased use of electrical cars and the factories that are producing those batteries. So digital tools and reliable decision support is already a necessity for the operation of the electrical power system. The energy transition brings big changes and requires to act faster and from a better perspective of all the dependencies and prerequisites on the system. In a bigger picture, this means that the industry has to cooperate effectively and with security in order to mutually maintain such a critical system as the Swedish power system is. A requirement for this is that information and data is collected, handled securely, and processed and shared between the different parts of the industry. And we can see that a digital change is needed to practically coordinate between multiple actors of new digitalized facilities, system services, and market solutions in a more complex, coordinated European electrical power system. When talking about the digitalization of the energy transition, we need to look at the big picture. This picture here illustrates the two parts of the electrical system. One is the commercial, acting through the electrical power market, as seen in the top, and the other is the physical one of the power system. Analysis, decisions, and control need to take both into account and deal with all their prerequisites and dependencies. Further into the future, it is probable that the power system is mainly controlled through automatic abilities from both central and local abilities. And in the near future, the tools developed are to be used as aid by the people in the control room. The digitalization can help us handle smaller margins. However, it increases the risk of system collapse due to bad data and architecture and manipulation of running algorithms. Svenska Kraftnät's goal is to make sure to keep this risk under control and responsibly and effectively digitalize alongside the actors of the power system. To face these challenges, the Nordic countries are developing a new Nordic balancing model called NBM. And the plan is to balance the entire Nordic synchronous area in smaller bidding areas. Does any one of you know what a bidding area is? Yeah. So, you probably know that electricity prices are higher in the south of Sweden than in the north. This is due to the division into bidding areas with different markets and amount of production, consumption, and transmission capacity. Sweden is divided up into 4 bidding areas, as seen on the right image. This is in line with the new harmonized European method of exchanging reserves. The automation of new balancing model gives us a greater proactivity for countering the volatility of renewable energy sources. And the model also aims to create a correct prices for ensuring that there is enough reserves in each of the bidding areas. This creates a big change in the balancing process. Today, the control room makes phone calls to activate a frequency reserve when they have found an imbalance. And this is a reactive way of work. In the future, we will work proactively and activate reserves based on a forecast on the future imbalance. And this is what me and my team are working on. The tool we are developing will be used to help the control room operators to work proactively instead of reactively by helping them knowing more about the imbalance ahead of time. And the imbalance forecasts that we make are created by using different types of machine learning algorithms and several different data sources and processing steps. We know that multiple things affect the imbalance. For example, wind power production, energy consumption, and calendar data. For example, if it's a weekday and people are working, while on the weekend they are not, they consume a different amount of energy. Or on the weekends, some factories might be closed, so that changes the energy consumption as well. The many different factors affecting the imbalance makes it hard for us humans to draw conclusions about the future imbalances. And using historical data alongside future plans and forecasts, we train models that can quantify the correlation between the different data sources. This model development is based on our knowledge of electrical power system and the market. When the models has been trained, we deploy them and then stream light data through them to make our imbalance forecasts. And as I've already mentioned, the data that we are trying to predict is imbalance. And we can think of a balance scale as a balanced power system. On one side, we have the energy production, and on the other, we have energy consumption. The two always need to be in balance to maintain the desired frequency of 50 Hz on the synchronous area. If production is smaller than expected or consumption is higher, an imbalance is created and needs to be rectified. And on the other hand, if the energy production is higher than expected or the consumption is lower, and the frequency will go up instead, and it will also cause an imbalance. So the goal is always to keep the frequency at 50 Hz while using as cheap and environmentally friendly reserves as possible. The imbalance data is defined by a few different data sources. A simplified calculation can be made by subtracting the planned flow and the total regulations from a bidding area from the measured flow of said bidding area. And the flow is just energy being exported from one area, for example SE1, to another, for example SE2. So the planned flow is the sum of all of the planned flows for the future in one bidding area. The total regulations are the sum of the activated frequency reserves of a bidding area, and the measured flow is the actual measured flow of a bidding area. And in this image, we can see an example of how the flow could look like in Sweden. The production is higher in the north, and the consumption is higher in the south. So naturally, the flow would look like something like this. There are different types of frequency reserves available. Some of them are very quick to activate, but more expensive or not as environmentally friendly. MFRR, the manual frequency reserve, however, takes a bit of time to ramp up, but is relatively cheap and good for the environment. The goal of having a good imbalance forecast is to be able to more accurately activate the correct amount of MFRR to keep energy prices down. So it takes about 12 minutes for the MFRR to ramp up. So the control room needs to know as much as possible beforehand of how the imbalance will look like to decide on how much they should activate. So therefore, we make forecast 2 hours into the future with a 5-minute resolution and deliver the forecast predicting the imbalance 15 to 25 minutes into the future to help them more correctly activate the correct amount of MFRR. Now I'm going to talk a little bit about the model framework that we developed to aid us in our development of imbalance forecasts. So a year ago, we were still developing inside a 3-year-old model framework with lots of limitations. Testing new ideas and implementing new models was both cumbersome, hard, and a risk for bugs. So we decided to try and create a new framework to help us be more flexible and aid us in developing better models. So what did we want from our new framework? Well, we didn't want a machine learning framework. What we wanted was a framework for configuring, training, and evaluating model structures specifically for our domain of work, which is time series in the energy business. And we wanted a model structure where we had information about data sources, transformations that will be done, and information about tests and a lot of other metadata. And we didn't want a machine learning model to be mandatory for our framework. So what challenges did we face when designing a good model framework? Well, we wanted it to be flexible so that it can easily be used to try new ideas and experiments and iterate over many things over a reasonable amount of time. Also, we wanted it to still allow quick rollouts of successful experiments and updates. We also wanted it to be possible for new data scientists without deep knowledge of system development to cooperate effectively and write reusable code. And it should be possible for a new data scientist to start working quickly without having to understand most of the framework. So here is an illustration of some parts of the old framework. And in the old framework, our model structures were defined in TOML files. So on the left, we have an example of that. And for example, we defined the features that we were using in the top and transformations of these features and which training parameters and models we want to use. And on the right, we have a display of what the structure would look like. So data sources and pre-processing as hole filling or outlier removal, operations, creating new features, aggregations for lagging the features, and then inputting it into a model for training or evaluation. And why did we choose to create a new framework then? Well, the old framework was way too rigid and made it very hard to implement new things. The different components were very connected. So trying to make an update in one place made it hard because you had to update in many places. For some model structures, this became too complex, and for others, too simple. Not only did it become difficult to test the models by themselves, it also became difficult for new developers to start working with the framework, as you all had to understand almost everything to work on just a few things. And this led to a lot of patchwork and spaghetti workarounds and a lot of headaches for the data scientists. And the use of TOML configs made it very hard to build complex models. So we ended up having lots of unused features that we still needed to maintain for other things to work. So what did we decide upon for our new framework? Well, we didn't want any limitations for the structure of a model. We wanted every part of the structure to in itself be able to be a complete model. And all of the structures are comprised of two types of nodes. So the first one is the data node, which contains metadata about a data source, for example, which data we want for which locations and which time periods. And the second one is the transformer node, which takes data from a data source or from an output of another transformer node and transforms it. And the data node, we didn't want it to fetch the data itself, only define what is needed. That is because we wanted it to be possible to have in a different process when running live. And in addition to the node classes, we also have a model class that, for example, facilitates orchestration. And what is done within fit and transform is not something that we really care about. All that we care about is making sure that what comes out of it is a pandas data frame. This means that everything could be implemented in one single node. Here we see an example of different nodes and their inheritance and parameters. So the node class have an output resolution defined, for example, and the data node has the output resolution and locations defined. While the transformer node needs to have, for example, a list of its parents and at least a transform function. And the model class contains information and functions used to orchestrate a model for training and evaluation of a specific target source. And we also have names for our nodes, so the parameters can be set easily, no matter how deep in the network we are. And here we can see a command for setting the alpha and gamma parameters for certain models during a tuning and how it would look like. And here we now have an example of actual code from our framework and the reuse of nodes within other nodes. So on the left, we have a structural imbalance node, which just takes two pre-processed features, planned flow and planned production, for their specified locations, and then transforms them to create a new feature called structural imbalance. And on the right, we have the gloomy kid imbalance forecast, which in turn takes the structural imbalance feature created on the left, as well as the past lagged imbalance internal features, and puts them into a scikit ridge model for training and evaluation alongside a future lagged target of the imbalance feature. Since models specify their own parents, we have the ability to tune the structure of the network, for example, by removing a feature. This is not possible in, for example, the architecture that scikit-learn provides. Here is an example of how we could choose to include the production smoothing feature or not in the forecast with internal target feature by turning on or off the production smoothing flag. So here is a graph example of how the forecast with internal target that we saw here is structured. The different input features as planned production and planned flow are fed into the scikit ridge node, and as well as the imbalance internal feature, which is the target feature. The imbalance internal feature is created by taking the imbalance feature and system regulation feature, pre-processing them and transforming them by subtracting the system regulation feature from the imbalance feature. Then the imbalance internal feature training data is past lagged and the test data is future lagged and fed into scikit ridge model. The output of the scikit ridge model is then transformed alongside the future lagged system regulation feature by addition to finally create the forecast with internal target feature. As you can see, this is a bit complex structure, but thanks to our framework, it was easily implemented as seen this in the previous slide. Oh, wait. Here. So this is the same thing. And the framework allows us to easily implement different types of nodes and then combine them in more complex ways without much effort. In this example, having 6 different input features with the respective processing, operations and aggregations, training and evaluating model, and then finally adding a post-processing step to finish it up. So how do we measure how well a model of ours is performing? We use a metric called rest imbalance. It is defined as the remaining imbalance during a specific time step that is left after a manual frequency reserve has been activated for said time step. This basically means that it measures how accurate our forecasts actually were for each time step on average. Lowering this metric has significant impacts on the energy prices. And by using our new framework, we managed to quickly iterate through lots of our ideas and leading to increased imbalance forecast performance. In the image here, we can see rest imbalance and the 95th percentile of it as the blue and red vertical bars, respectively, for each bidding area, as well as the total Sweden. And the green horizontal bar represents the benchmark value that we are supposed to beat. As we can see, we managed to pass the benchmark on most bidding areas and the sum of Sweden, which we were never able to do with the old framework. We still have lots of ideas that we now more easily can implement to further reduce the rest imbalance, as well as minimizing possible risks for example, for errors due to bad data and model degrading. The new framework has enabled us to improve on the imbalance forecast by making it easier to implement our ideas, and has sparked our imagination to try more ideas by making it both easier and more fun and rewarding, thus helping us making a better tool for aiding the control room and help Sweden and the Nordic countries to better deal with some of the challenges that the renewable energy transition that is currently taking place brings. Thank you very much for listening to me. If you have any questions, you can ask them now, and I will do my best to answer them. And we also have our booth out there, so if I can't answer them, maybe someone out there can.
Thank you. Thank you for your talk.
Yep.
I had a question about how you run your nodes.
Yeah.
Do you have like an orchestrating platform?
Yeah, we run them on OpenShift. Yeah.
Thank you.
I had a question.
Thank you. I just have a simple question. How does, I guess, the data scientist and the dispatchers of electricity interact with each other? Do you simply hand over, I guess, the prediction in the 2 hours and then they handle this from now on? Or is it, how are the interactions basically?
Yeah, like currently we're just sending them to them, and they're looking at them and using them like as aid, or
All right.
that's the first step. And then in the future, like it's planned to automate this, so it runs completely automatically, or almost completely at least.
All right. And just, I also have another. How do you handle, I guess, events, special events? I guess sometimes you can, how do you deal with it in your models? And how do you integrate them?
Yeah, so some of it, we like, that is a huge issue for us actually. So we have been in lots of discussions with the control room and trying to figure out how to handle like special events, if they should like do some, send some message that a special event has happened, or if we should be able to detect it immediately. And what we have decided is to try to make like both work as much as possible. We want it to be automatic, of course, because it's easier and less prone to like human errors. But for some cases, it's hard and might not be possible now, at least. So yeah, a mix of adding manual input and automatic detection, and sometimes some events are even hard to manage at all.
Okay, one more question here. So you do a forecast, right?
Sorry, Oh, okay.
So if I understood correctly, you do a forecast of the energy consumption, right? So and you train your model, but do you use real-time data when doing forecasting? For example, I don't know, outside temperature, weather forecast, or I don't know, wind speed or something like that.
Yeah, so our main forecast is imbalance forecast right now, but we're like also working on both wind power and consumption forecast, for example, both as standalone and an input to our imbalance forecast. And yeah, so I'm not sure if that was the full question.
Yeah, kind of. And one more. So, okay, you train your model, right?
Yeah.
What is your input data in that case?
So we have lots of different input data. One of it is the imbalance that we had in the previous steps. And then we have like calendar data, planned production and planned flows. We can have like other types of forecasts as mentioned.
Yeah, so that was my question. So do you combine your historical data from the past
Yeah.
and the real-time data?
Yeah, exactly. We combine real-time and historical data and also future plans. And we plan to like also include both our own and maybe external forecasts as well. So both like it's running with real-time data, but it's using some historical data as well and some future data.
Okay, thank you.
Hello? I'm right here.
Yeah.
Thank you for the talk. It's super interesting. Like, this is something that we do a lot in the steel industry at my company, so this is like spot on. So thank you. It's super, super interesting. I have two questions that kind of go hand in hand. The first one is, I didn't quite understand like how often you actually do the predictions, because you said it was like forecasting 2 hours ahead with a 5-minute interval, but then you said it was like 15 to 20 minutes that you're actually predicting. So like, how often do you do the prediction? And then, yeah.
Sorry.
And the second part of that is also like, how do you handle like retraining the model? Like, are you training the model online, and like how often you do that? Do you have triggers to say we have data drift now, so we need to retrain it, or is it like schedule, say that you retrain it on a time period, or how do you approach that?
Yeah. So for the first question, we're doing the predictions for 2 hours into the future with 5-minute interval or resolution. So we're doing it every 5 minutes.
Okay.
But the control room only needs like the 15 to 25 minutes to like decide how much of the reserves or the MFRR that they need to activate. So that's the most important
Okay, got it.
part of the prediction. But we're still like doing it for a longer time period.
Okay.
And for the second question, we're currently just manually retraining, but for like when it's fully deployed, we have to find some solution to automatically retrain it if needed. And we haven't like decided on an interval or like if it should be done once a month or every week or even less often than a month. We haven't decided on that, so.
Okay.
Yeah.
Okay. Thank you.
Was that all the questions? Oh, a question here.
Hey, yeah, I had a question about I didn't understand the forecasting part. So you forecast 2 hours ahead
Yeah.
in 5-minute resolution.
Yeah.
Does that mean that you take the output of your prediction and use it as an input again and keep doing that?
No. No, we just use like the live data and previous time steps.
Okay.
And like plans for future data, but we don't at least currently use the prediction itself as an input to.
Okay, so your prediction is it's 2 hours, and then you have, I guess, at each 5 minutes there's a value.
Yeah, and then
okay.
and so every 5 minutes we make a new 2-hour prediction.
Yeah.
So it will be an overlap of predictions, of course.
Yeah. So it's not regression, I guess, that you're doing?
Yeah, I think it's regression.
It is regression,
Yeah.
but you have this 5-minute interval for 2 hours ahead.
Yeah.
Okay. Okay, thanks.
Hello. It's here.
Yeah.
Thank you for your talk. I have a question about resources. I mean, how much CPUs does it take? I mean, if you're doing this every 5 minutes, how much memory do you take? How much does it cost? I mean...
So I'm not actually quite sure about that, but the operation is not very heavy. So I think we have like a lot of spare time for running. It's not like it's almost not enough time. I don't know the statistics actually about that, but probably Jakob on your left knows that. Yeah, okay. Yeah. Yeah.
You can answer, you know.
Okay, so we use quite simple algorithms right now. So we use linear models, and the prediction is quite fast. It only takes a few seconds, but we're looking at more advanced libraries and deep neural networks and stuff like that, and then we will definitely need some more compute. But currently we're okay. Yeah.
Yeah.
So I don't think we have time for more questions right now because we have the next speaker, but I guess you will still be around at the conference for more questions.
Thank you.